So mutations are any change that you have in the DNA. A becomes T, C becomes G, something like that. Any little change is a mutation. And I hate to tell you guys this, but you are all mutants. You all have mistakes. Think about it. You have 300 million nucleotides in each of your chromosomes. You have 46 of them. It's impossible for your cells to copy your entire genetic code without making a mistake here and there. It happens. It happens. In fact, the longer you're alive, the more mistakes you're going to have. So I'm a bigger mutant than you guys are. So mutations happen. They're changes, they're mistakes in the genetic code, and they're a fact of life. It happens. Today, we are very specifically talking about point mutations, because there are other types too. Oops. Sorry. So point mutations are change just one nucleotide. A becomes G, C becomes T. Whatever that one mutation is, just one nucleotide. Again, later in the year, we'll talk about chromosomal mutations. That's where you have a mistake with like an entire region of the chromosome. Huge section of the chromosome gets mutated. And that can be drastically different than just one nucleotide. And by the way, this is the coding strand. So if you guys remember, we did our 2 strands of DNA. We had the template strand and we had the coding strand. The template strand is what the mRNA is actually paired with to be made, but it's going to be a copy of the coding strand. So this is the coding strand. Here's our initial sequence. Oh, yep, quick reminder, first lunch bell there, guys. If you brought a snack, I know it's a long time to lunch. I've been telling you guys, if you brought a snack, feel free to kind of get it out and munch at it quietly at your leisure if you like. All right, so here's our DNA coding strand. Here's our coding wheel. So A, U, G. Methionine. Again, that's good. That's our start codon. Just have to write the first 3 letters, M-E-T. GCC. Alanine, my favorite. TGC. Again, in RNA, it should be a U, not a T, so we'll start with U. So U, G, C, U, G, C, cysteine. AAA, lysine. CGC, arginine. TGG, again, T should be U, so U, G, G, tryptophan. All right, so there's our normal strands. Let's take a look at types of point mutations. First type, substitution, which is exactly what it sounds like. So again, exactly like it sounds like, a substitution has one nucleotide taking the place, substituting for another one. Now, there are three different things that can happen, three outcomes you can have from a substitution. First, it's called a silent mutation. Hey guys, quick pause. Too many of you guys have your cameras too far up or down. I need to see you in the screen or count you absent. So adjust those cameras so I can see you. You guys are fine. You guys can turn the cameras off if you want. You don't have to, but I know you're here. You're not hiding from me or anything. Silent mutations have no effect. So you guys notice the difference? It was GCC, now it's GCT. Let's see what effect that has. Now, for the most part, everything's the same. So this is still met. That one didn't change. But now we have GCTs. We do have to use this. All right, so G, C. Again, U in place of T. Huh. Didn't change. Didn't change. So that's what's meant by a silent mutation. Nothing happened. This one is still the same. This is still cis, lis, arg, and tryptophan. So again, nothing happened. We had a mutation, we had a change, but nothing happened. Silent. You'd never even know it's there. Kind of like a tree falling in the forest, and no one's there to hear it. Silent. We could also have missense mutation.
You're off the page.
Oops. Thank you. You guys probably had some of these missense mutations in your LT4, the activity you guys did on Friday. One little change, one amino acid, or in the case of the activity Friday, one little letter. Your whole word may not have been messed up. You still might have gotten the gist of the word, but you did have that one little change in there. That's called a missense mutation. Take a look at an example of that. Somebody's watching something exciting. All right, so there's our one substitution. It was TGC, now it's GGC. So let's see what happens here. Again, this one's going to be the same. We have MET. This one's going to be the same. So we ALA. Let's see what that GCG does. G, C, G. Hey, my fave. But that's not what it was. It's different. In fact, I should probably make that in red. The rest of it's still the same. Lis, arg, and tripped. So again, it's one error. Now, is that error a big one? I don't know. It depends on the protein, depends on the amino acid. You guys saw, hopefully you saw when you did LT4, sometimes that one little change is actually beneficial. It's actually good. Like I think one of the words you guys did started off as hallow and then became hello. So it actually made more sense after the mutation. That's possible. I'd say it's not as likely, but it's definitely possible that happens. Another example actually is, well, you see it in your homework tonight, is insulin production. People who are diabetic have just one amino acid difference, just one little mutation, and voila, their insulin produced isn't the right shape. So kind of depends how integral, how important that amino acid is and how big the change is to see how much of an effect it is. Questions so far?
Wouldn't GGC be glycine?
Oh, it is GGC. I did GCC. You're right. GC is glycine. Well, that's problematic. Good catch. Good catch. Still not the original cysteine. So still not accurate, but yes, it should be glycine. Good catch. Other questions? Another type of substitution mutation is called a nonsense mutation. A missense, again, oftentimes like you guys experienced in that activity you did over the weekend. A missense mutation, you can oftentimes still kind of see what the word is. The protein still has its basic function, its basic job. But a nonsense mutation, now we've got a non-functional protein. Now we've got a protein, this is not how it's supposed to be. Usually nonsense mutations are a mutation to the stop codon. Maybe they add a stop codon before there should be one. Or maybe it's a mutation to where the stop codon is, and now you don't stop. You just keep reading. Either way, you're going to end up with a protein that's either really, really short, like way too short, or a protein that's way, way too long because you either stopped early or didn't stop when you're supposed to. Either way, it's a bad, bad thing. You're going to end up with a protein that is non-functional. Again, AUG, all right, that hasn't changed. MET, GCC, that hasn't changed. ALA, TGA, let's see what that is. Again, T should be U, so U, G, A. Ooh, there we are. There we are, a stop codon way too early. And guys, when you read a stop, you stop. That protein's done. I know you can argue, well, that's still the same codon as it was up here. Yeah, and that's the, but it doesn't matter. They're never going to get read because our ribosome is going to read stop and he's going to stop. Questions? Cool, cool, cool. All right, so all of those are substitution mutations. Those are all substitution mutations, but we can also have insertions and deletions, which again are exactly what they sound like. So these are a special type of, both of them are a special type of mutation. So both insertions and deletions are a special type of mutation that we call a frame shift mutation. And the reason why is because they shift the entire reading frame. So a common example of a shifted reading frame something we can all very easily read. Three-letter words, a sentence made entirely of three-letter words. Why three-letter words? Well, because in genetics, all of our words are three-letter words. Codons, right? They all have three letters. So nice three-letter word sentence there. That makes perfect sense. I mean, we don't know why we're talking about a fat cat eating a rat, but we can all read it. We all know what it's saying. The fat cat ate the rat. What happens if we have a frame shift? Ah, see the deletion? That's going to shift everything. So our entire reading frame just got distorted. That's a frame shift. You can see how terrible this is. Our once sentence that we could read, just the whole thing gets messed up by an insertion or a deletion. So see our deletion there? We lost the letter from our initial strand. So when we go to read this, our entire frame is shifted. There's a new codon. There's a codon. There's a codon. There's a codon. Our entire frame got shifted. So AUG, that hasn't changed, met. But now instead of having the G, C, C, we have GCT. Well, okay, that hasn't changed yet. So far, we're okay. Now, GCA. Oh man, I like this protein so far. Now we have AAG. GCT. Man, I really like this protein. Our entire reading frame got shifted. All of our amino acids are out of whack. Not good. This is not going to be the protein we're trying to make. Same thing on the other end. If you insert one, and there's our inserted protein or inserted nucleic, inserted nucleotide. And again, that has shifted our entire frame. We now have a whole different set of codons. All right, so these first two are okay. These are still the same. But now we have CTG. We've inserted that new letter. So C, again, U for T. G, that'd be leucine. CAA. Glutamine, GLU. AGG. Arginine. And CTG. Leucine. So again, we've completely messed up our entire reading frame. Just one little letter, and the whole thing's thrown off. Pretty bad. We are not going to have an operational protein then. Certainly not going to do what it's supposed to do.
What happens to the extra nucleotides, like the extra Gs?
Yeah, good question. So I mean, obviously I don't have enough room to keep going. Otherwise I would. If you were a ribosome reading this, you would go until you read it stop, which might be really, really early, or it might be really, really late. But yeah, your entire reading frame is going to be shifted. Good question. Other questions? let's finish these up then, huh? So first thing, very important to note that mutations only happen in DNA, not in RNA. That isn't to say mistakes aren't made in RNA. They are. Mistakes are definitely made in RNA, maybe even more so than in DNA, but we don't call them a mutation. RNA, you have hundreds, thousands of them per gene. So what if you make a few bad proteins because of a mistake in the RNA? It's okay. You guys remember we did translation, we diagrammed it, and we drew a whole bunch of the RNA polymerase? There's like 4 of them all transcribing or translating the same gene. Yeah, well, you have hundreds, maybe even thousands of mRNA strands each time you're translating a gene. Make sense? DNA, mutations happen every copy you're going to make. Is going to be messed up because your DNA is messed up. But with RNA, who cares if a copy gets messed up? It's just a copy. Read who it is. Stay on the line longer. All right, sorry about that, getting phone calls, but it's like half a mile away. So we are. So mutagens, mutations only happen in DNA, not RNA. RNA is just a copy. Just out of curiosity, they just try to call me. Mystery solved. It hung up like the second I got back here and picked it up. So any substance that causes a mutation is known as a mutagen. And again, we don't need any more environmental causes than what we already have. Our cells aren't perfect. They're close. They're close. If you can type 1,000,000 letters in a handful of minutes and not make many mistakes, that's pretty close to perfect, but they're not completely perfect. They still make some mistakes. Unfortunately, there are things out there that cause them to make even more mistakes. So common examples: sunlight, X-rays, cigarette smoke, even some viruses are mutagens. These are all things that potentially can change your DNA. They can make your DNA change letters. Often when it's duplicating, that's usually the most common time for a mistake to happen. During S phase, you're duplicating your DNA and just get a wrong letter and make a wrong base pair. All right.
You're off the page.
Almost there. Almost done. One of my favorite things in all biology, perhaps because of the name. The wobble effect. It's a fun little name. Here's the concept of the wobble. "20 amino acids." I don't know if you guys remember that from the beginning of the year. I'm guessing I threw it out there, probably didn't hammer it home very hard, probably didn't make it very important. But there are 20 different amino acids, 20 possibilities. Those of you who are excellent at math have probably already recognized that a codon, or a codon has 3 letters, and there's 4 possibilities for each letter: A, T, C, and G. Means that 4 times 4 times 4, 64 potential codons. So only 20 amino acids, but 64 possible 3-letter bases, 3-letter combinations. So many codons code for the same amino acids. Which again makes sense. They have to, right? There's only 20 amino acids, but 64 possible codons. For instance, if you take a look at your codon wheel and you start off GU, look, it doesn't matter if you go GUG or GUA or GUC or GUU. It doesn't matter. They're all going to code for valine. So as long as you get GU, last letter doesn't matter. Yeah, I'm actually making a video right now. So as soon as it's done, I'll turn into a YouTube, post it, and by the time you get home this afternoon, it should be up. Yep. All right, so there we go. Again, my favorite thing, probably because it's the name, but also it's really cool. This is what's called the wobble effect. Basically, because as long as, well, oftentimes, as long as you get the first two letters, you're going to get the third one. It's like nature's defense against mutations. Okay, is it perfect? No, it's definitely not perfect, but again, it definitely limits the effect that mutations have. Even if you get your last codon mutated, you're still going to get the right amino acid. And that's called the wobble effect.